In this video, we're going to answer all 5 of these function analysis questions, just like the example we did in the notes, with another function. I'm going to film 3 different videos like this just so you have 3 additional examples to look at on top of the one that we did in class on, what day was that? Right before Thanksgiving, whatever day that was. All right. First thing I'm going to do with this is find the first derivative, and then I'll be able to answer the first 3 questions using the first derivative. After I do that first derivative sign chart, then I'll work on the second derivative and make a second derivative sign chart to answer the next 2 questions. This function is going to require the chain rule in order to find the first derivative. It does not require the product rule though. So the first thing I'm going to do is rewrite the function as parentheses with a 1/3 power instead of a radical. This makes it easier to use all of our derivative rules. And then I'll use the chain rule to find the first derivative. This is a little quicker than the example we did in the notes because it's not a product rule. So I'm just going to bring the 1/3 down, keep the inside the same, subtract 1 from that exponent, and then multiply by the derivative of the inside. And then if I simplify that, this is going to be a 2 on the top and a 3, and then all this parentheses on the bottom. So the 2/3 power there on the bottom. So there's my first derivative. Next step is to find critical points. Now remember, to find critical points, we want to know where is the derivative equal to 0 and where is it undefined. Well, in order for the derivative to be equal to 0, the numerator would have to be 0. There is just no way that you can have 2 over something and have that be equal to 0 in the end. It's just not going to happen. So it's something that we should check, is to say y prime equals 0, but there's no solution to that. So we'll just move on to the second part of finding critical points. And that would be where y prime is undefined. And that would require the denominator to be equal to 0. So we're going to say 3 times 2x plus 1 to the 2/3 power equals 0. Well, you can imagine dividing both sides by 3 to get rid of that 3. There's still a 0 on the other side. You can imagine taking both sides to a power to get rid of that power. It's still a 0 on the other side. So really this boils down to 2x plus 1 has to be equal to 0. It's really just the inside of the parentheses to be 0 is the only way that's going to work. And then if we solve that, negative 1/2. Step 3 is to make my first derivative sign chart. And I've only got 1 critical point to put on my sign chart. To build the rest of the sign chart, I need to look at my first derivative. So I need to say, if I plug in something on the right side, is this first derivative over here going to be positive or negative? Well, an easy number to plug in on the right side is 0. If I plug in 0, that's going to give me 2 on the top. It's going to give me 3 times 1 to the 2/3 power, so just 3 on the bottom. A positive on the top, positive on the bottom, gives me a positive. So everything over here will be positive. And this is a first derivative sign chart. So make sure that we label this because we're also going to do a second derivative sign chart in a minute. And then if I plug in something like negative 1,000,000, well, that 2 on the top is still going to be a positive 2 on the top. And then I imagine plugging in negative 1,000,000 to the bottom. This is going to be negative 2,000,000. I'm going to square it, and that will make it positive. And I'm going to cube root it, which would still be a positive, and multiply by 3. That's still positive. So because of this power of 2, this 2/3 power, it's a square and a cube root, it makes everything positive. So no matter what we plug in there, we're going to get a positive first derivative. So this is something a tiny bit unusual, where it's positive on one side, positive on the other side, undefined right in the middle. But if we think about what we know about cube root functions and what they look like, they tend to go like almost vertical right there in the middle. So that's what's happening here is right in the middle, the tangent line becomes straight up and down vertical. And a vertical line has an undefined slope. So there's going to be just one instant in the middle where it's undefined, but everything else it has a positive slope because this is increasing, increasing vertical, and then still increasing, increasing. So that's what's happening there. If you thought that was a little bit strange, that's the reason why. Now we'll be able to answer our questions. Now, the first question they're asking in part A is, where does this function have a horizontal tangent line? For horizontal tangent lines, we're saying, where is the slope equal to 0? Or in other words, where is the first derivative equal to 0? And we already said the answer to that has no solution. So if there's nowhere that the derivative is equal to 0, then we're not going to have any horizontal tangent lines. No horizontal tangents because the first derivative is never 0. The next question they're asking is, where is this function increasing and decreasing? We can see that in the sign chart. A function is increasing when the first derivative is positive, decreasing when the first derivative is negative, and this one has a first derivative that is positive all the time. So we're going to say this function is always increasing. So I'm writing y is increasing on the interval from negative infinity to infinity. The entire real number system, y is always increasing because y prime is always positive. Now that's probably enough, but if there's a question that is specifically asking where is y decreasing, then you would need to say y is never decreasing because y prime is never negative. Now the last question, or the third question being asked here, is find the relative extrema. So what's happening here is we found out that this is increasing and then still increasing on the other side, and there's a brief moment where it's vertical in the middle there, but a vertical does not give us a max or a min. A max or a min happens when your function changes from increasing to decreasing or changes from decreasing to increasing. And so we're not going to have any relative extrema in this one. Remember, the thing to look for is a critical point with a sign change. And we do have a critical point here, but there's no sign change happening. So no sign change means no max or min. So there's the answer to the first three. For the next couple of questions, we're going to use the second derivative. So I'm going to sort of go back here and put step number 5 right here. And we're going to use what we had up here for the first derivative in order to find the second derivative, but I'm going to write it a little bit differently. So I'm going to kind of ignore this step for now. I'm going to look at this step in here. I'm going to say y prime. All I'm going to do is combine this 1/3 with this 2. Y prime equals 2/3 and then parentheses 2x plus 1 to the negative 2/3 power. And now this is just a pretty typical chain rule type of problem to take the derivative. So the first thing I'm going to do is bring down this negative 2/3 to find the second derivative. So 2/3 times negative 2/3, and then keep the inside the same and subtract 1 from this exponent. So negative 2/3 minus 3/3 will give me negative 5/3. All right, so what I'm ending up with here is this will be my numerator, and all the rest will be my denominator. So I'm going to have a negative 4 on top. I'm going to have a 9 and 2x plus 1 to the 5/3 on the bottom. Then I'm going to sort of just follow the same couple of steps here with my second derivative instead of my first derivative. So number 6, we don't call them critical points, but we're going to find the places where the second derivative is 0 or undefined. And just like before, if there's nothing in the numerator to set equal to 0, it's just a constant, is never going to be 0 in the numerator, then to say y double prime is equal to 0 is not going to have a solution. There's nothing that's going to make that 0. So all we're interested in this time is going to be where y double prime is undefined. And that will require the denominator to equal 0. And just like before, that just requires this 2x plus 1 to equal 0. And so negative 1/2. We're looking at a very similar sign chart, but be careful, it's not going to be identical because we're going to be plugging numbers into the second derivative instead of the first derivative in order to determine whether it's positive or negative. So that'll be our next step. Step 7, second derivative sign chart. So I want to plug in, on this side we'll plug in 0. We're going over here to the second derivative. So this gives me a negative 4 on the top, and on the bottom I'm going to get 9 times 1 to the 5/3. That's a negative on the top, a positive on the bottom. It's going to give me a negative value. So you didn't have to really plug everything in and do all of the arithmetic in order to figure out it's a negative value. Now let's imagine plugging in negative 1 million. It's going to give me a negative 4 on the top no matter what. And then on the bottom, I'm going to have a 9 times some negative number to the 5/3 power. So let's think about what that 5/3 power does. Raising it to the 5th power, it will still be negative because 5 is odd. Taking a cube root is okay because 3 is odd. So we can take a cube root and it will still be negative. And so this is going to give me a negative number over a negative number, which in the end is a positive value. So undefined at negative 1/2, but it's a positive second derivative to the left of that, and it's a negative second derivative to the right. So what that tells me, it's not about increasing and decreasing this time. It's about concave up and concave down. So what we know is that this is increasing all the time. So to draw my symbols really like this, it's not really accurate because when I draw those, there's places where it looks like it's decreasing, which we know it's not. Really what's happening is this concave up part looks like this. And then remember we have that vertical piece, and then the concave down part looks like this. So it can be concave down and still be increasing the whole way. And that really kind of models what we know cube root functions look like, which is what this function was in the very beginning, if you remember up there. So everything that you know from every math class you've ever taken should all kind of line up here. If there's ever something that seems fishy, you're going to want to go back and check your work and make sure you didn't make a mistake anywhere. Now we can answer the rest of the questions. So question D says, where's the function concave up or concave down? E is inflection points. So we can say y is concave up on this first interval because the second derivative is positive. Now I'm not going to make you watch me write all of that, so pause. Okay, I paused in order to write it. You should pause if you need a minute to read this and interpret it and wrap your mind around where it all came from. But y is concave up on this left interval where we know that the second derivative is positive. And the short way to write y prime as positive is just y prime greater than 0 on that interval. And then the flip side of that same coin, y is concave down on the interval from negative 1/2 to infinity because y double prime is less than 0 on that interval, or is negative on that interval. The last question we're asked here is to find inflection points. Inflection points are places where the second derivative changes sign. So it's where the concavity changes from up to down or from down to up. It doesn't matter. If we're talking about the first derivative, it matters whether the first derivative was changing from increasing to decreasing or decreasing to increasing, because that will be the difference between a max or a min. But we don't have two different types of inflection points. We don't care what direction it's changing. Any kind of sign change in the second derivative will be called an inflection point. So your inflection point is that -1/2 number. So there's the answer to your last question. Y has an inflection point at x equals -1/2 because y prime changes sign there. Now we want to get all of these because lines in the notes because it'll help you, if it's in your notes, it'll help you know where to look when you're doing another problem that is similar but different. The other reason is if there's ever a question that says justify your answer, how do you know this? This is what you need to be able to say. It's because I looked at either y prime or y double prime, whichever one is appropriate, and I saw that it is positive, negative, 0, whatever is appropriate for that question. That's how you need to sort of phrase your reasoning for those. So kind of look at the lineup of all of these steps. We found the first derivative, we set it equal to 0, we found where it's undefined, which was really just numerator is equal to 0, denominator is equal to 0. We made a sign chart with the first derivative, and then we answered some questions using the sign chart. And then we went back and did all of those same things with the second derivative, and then answered the last two questions with the second derivative. So notice the similarities, but also the differences between what you're able to do with the first derivative and what you're able to do with the second derivative. That's the most important thing for you to just memorize, is which of these things require first derivative, which of them require second derivative. If you know what it is you're supposed to do, doing the steps is really a matter of algebra rather than calculus. The calculus is all in the interpretation in problems like this.